Hello, everyone. I guess this is the crowd that didn't party yesterday night. So my name is Ishwar Bala. I'm an engineering manager in AWS. My team is leading the EKS effort that we announced this week. And this session is going to be a deep dive into EKS, which is the service we announced. It'll be how many of you here know about Kubernetes? Show of hands, please. Cool. I do see a few who didn't raise their hands. If you have more questions, I'll be happy to take it after the session. OK, so what's going to be our agenda here today? I'll do a little bit of introduction about what Amazon EKS is, talk about how the networking in EKS works, how we've integrated VPC networking into Kubernetes. And then I'll go on to talk about how IAM authentication and authorization works in EKS as well as in regular Kubernetes. And then I'll go on to do a demo. So for those of you who missed our announcement this week, and we also had a session by our product manager, Brandon, who's going to be here after the speech here. So we announced Elastic Container Services for Kubernetes. And to begin with, we'll be managing the Kubernetes control plane for you. So I want to clarify a little bit about the tenets we've built our service around. So we've heard from customers that they love Kubernetes and love using Kubernetes on AWS. And they'd like to see the entire experience translate well when we move on to into the service, right? So there's no better way to do that than just take Kubernetes and offer it to customers rather than do anything else. And one of the things we really want to do here is be good community citizens, which means that we don't want to be managing private forks. We want to be native Kubernetes. We want to be upstream Kubernetes. And you'll see us engaging more with the community to make Kubernetes run well on AWS and in general, delivering towards Kubernetes roadmaps. And the other thing we wanted to do is we have a wide segment of customers. We want to make sure that we support all sorts of workloads, like small, big enterprise workloads. What that translates to is bring the operational security and the reliability that customers love AWS for into operating this Kubernetes service, right? So we've learned a lot. We have an existing orchestration system in ECS. Customers love it. It scales unbelievably well. One of the most secure, reliable, strong operational service in our portfolio, right? So we want to bring that experience and into managing and operating this Kubernetes services for our customers. And the last thing we want to do is we want to make sure that, so customers also told us that they love running Kubernetes on AWS. In fact, according to the CNCF survey, the vast majority of customers who use Kubernetes in a cloud provider actually use it on AWS. And that's directly because customers love the breadth and depth of services we offer, right? So we want to make sure that all of these services continue to work well with Kubernetes and also with the service we are offering here, right? But if customers choose not to use the AWS services, we also want to make sure that the native Kubernetes experience continues to work and is not broken in any fashion, right? So, OK, so what does EKS provide you today, right? So we manage the Kubernetes control plane for the customers. What that means is we manage the master, we provision the masters and also the cluster coordination store in Kubernetes, which is etcd, in a highly available fashion across multiple AZs for you, right? So we are going to offer upgrades as and when new releases of Kubernetes make it through the community. So as EKS customers, what does the experience look like, right? So you come into the EKS console or use the AWS CLI. You would create an EKS cluster. And when the EKS cluster creation completes, what you get is a master endpoint, right? All of the infrastructure behind that master is completely abstracted for you. And you would continue to interact with this particular master endpoint using kubectl or the worker nodes. Or any other tooling you have, right? So then you would go on to provision your worker nodes. So in our model right now, you bring your own worker nodes, which means that you would create your EC2 instances, pass in the master endpoint that we gave you as part of the EKS cluster creation, and then point your nodes at that particular master, right? And then everything works seamlessly. You can launch as many, whatever add-ons you're using today. There's no restriction, and then you can continue to launch your application workloads. So I want to talk a little bit in depth about what's happening behind the scenes when you come to create a cluster. So you come into the console, you create a cluster. You'll see what happens when you create a cluster as part of the demo. So you're able to pick which Kubernetes version you want, and you'll be giving us a VPC ID as well as a role arm. This is because, given that the worker nodes are now running in your account, we want to know which VPC or worker nodes are going to be running in. Number one. Number two, we want access in creating all the resources that you'll be launching as part of your workloads, like, for example, load balancers or ABS volumes. So we'd go on to create the HA masters, and then we'll also go on to create a highly available HCD cluster. We'll go on to bring up all the infrastructure needed to use IAM credentials in our service. And then we also take care of all the certificate management required when you set up Kubernetes, right? Including the service account tokens that Kubernetes expects you to give. We auto-scale the masters for you based on the workloads we see, like how many nodes are connected at any given point, the pods running in your cluster, or the pod mutation rate, and so on and so forth. So we also provision a load balancer in front of this highly available master setup, which is the actual endpoint you end up getting, right? So the only thing from your perspective is that load balancer endpoint, and everything else is abstracted behind that. So that's basically the first section, right? So I want to go on to talk about the networking integration that we offer as part of EKS. We've come up with a new CNI plugin to make VPC networking integrate well with Kubernetes as well as now in EKS, right? So what is the benefit of this? Why would you use this over the plethora of existing solutions out there? In our implementation, what you get is an AWS routable IP address. Like, if you think of Kubernetes has certain networking requirements, right? For example, it's going to expect every pod to have its own IP address. The pods are in a flat network namespace, and the pods should be talking to each other without any NAT in the middle. So in order to make that, given that every pod gets its own IP address, with our networking plugin implementation, and given that we integrate VPC networking into Kubernetes, your pod is going to get a AWS native routable IP address. This is huge, right? Like, for example, you don't need to set, like, all the other existing AWS services can reach out into whatever is running in your Kubernetes workloads pretty seamlessly, right? We have so many in VPC services like Elasticsearch, EMR, right? Even the load balancer, right, can now just directly hit whatever is running in your Kubernetes cluster in EKS, in AWS basically, right? So it's a very, very thin shim at the end of the day, right? So we make the infrastructure possible, like attach and detach the ENIs, get the secondary IP addresses, and then we get out of the data path. We literally are not in the data path at all, right? So which means that you get the complete power and the performance of the VPC networking underneath. So in our implementation, every pod gets an IP, which is actually a secondary IP address from your ENI. So there are limitations for that because, for example, I think Brandon mentioned it as well, right? So the security group is actually attached to your ENI, so you can be as fine-grained if you would want at a pod level in this particular implementation. But I'll talk more about it a little later. So what makes this possible, right? So I want to talk a little bit about the existing network plugin infrastructure in Kubernetes. So Kubernetes supports this really nice pluggable network mechanism, and that is CNI, which is Container Networking Interface, right? So Kubernetes really doesn't allocate the IP address. It expects a networking plugin implementation to take care of that for you, right? So in CNI world, it need not be Kubernetes. It could be anything that's running on top that's using the CNI infrastructure, which is the runtime in this case. The runtime, whenever it has to do any particular networking activity, it reaches out into the network plugin, right? And then the network plugin takes care of provisioning all the networking mechanics and using whatever mechanism it wants to use, right? And then it goes on to, it just returns back to runtime saying, hey, I've set up this network. You're free to continue to whatever you want to do, right? So before I go on a little bit in depth about the network plugin, I want to talk about how you would end up using it. So it's not specific to EKS, right? So as mentioned, we want to make the experience for running Kubernetes on AWS pretty seamless. So it doesn't matter whether you want to use EKS or just want to use Kubernetes on AWS. So which means that this network plugin and anything else we work on, we want to make sure that it works well on EKS as well as any kind of Kubernetes cluster you want to bring on your own. So the way you would use it is a pretty simple daemon set deployment, right? So we have a YAML file, and then you can just go on to create this, do a create using this YAML file, which will deploy a daemon set, which means that the network plugin we have, all the infrastructure is actually deployed across all the nodes in your cluster, and then the networking works pretty seamlessly. OK, so a little bit about the networking internals, right? So like going back to the previous slide about CNI, you saw a runtime which is actually calling out the network plugin, right? In the Kubernetes case, that runtime is actually kubelet, right? And in our case, the kubelet, whenever it wants to create a pod, it reaches out into the CNI plugin. So you basically can have a configuration file which actually tells that this is the CNI plugin you should be invoking whenever you want to do networking, right? So when kubelet is about to create a pod, it reaches out to the VPC CNI plugin and then asks it to set up the networking, right? It says, add a network interface for me, right? And give me an IP address, right? So the VPC CNI plugin, what it does, it goes on to create the ENI. And it's not ENI per pod. So what it means is it'll allocate the ENI, and it'll allocate also the secondary IP addresses for the ENI, and then take one of those available IP addresses, and then give it to the pod, right? And wire up the pod to be able to use that IP address, secondary IP address. So which means that now the pod is directly into the VPC network with all the benefits I spoke about. So a little bit about the CNI plugin architecture itself. So in the previous slide, you saw that it was a one single blocks, which is like the VPC CNI plugin. But in reality, it's actually two different components. So kubelet ends up talking to our CNI plugin, which is actually a very thin layer. All it does is that it passes on the actual work to a network local control plane, which is another daemon that's running alongside in that particular instance. And what happens in the network so that network local control plane is the one that is responsible for actually doing all the ENA attachment, detachment, secondary IP address allocation, right? And maintaining a pool of the available IP addresses. And then when it finds when the CNI plugin reaches out to this control plane, it finds out which one's free and then gives it back to the CNI plugin. And the CNI plugin will end up wiring the pod to use this particular IP address. So I want to talk a little bit about the packet flow, how the packet flow in this particular CNI plugin ends up being from, let's start with the pod to pod, right? So if you think of an instance, right? So we have an EC2 instance. It's running an operating system, right? In Linux, you have a default namespace or a root namespace to begin with, right? We have an ENI in there, right? So whenever you launch a pod in Kubernetes, the pod gets its own view of the world, right? That includes the networking perspective as well, right? It thinks that it owns the networking space in there, so it gets its own network space. So what happens is whenever the kubelet reaches out to us and says that, hey, I want to set up the network for this particular pod, what we do is we create a pair of VETHs. And VETHs in Linux is a virtual Ethernet device, which is similar to, let's assume it's it's like a physical device, but that makes networking possible, right? And then what we do is we create a pair of it, and then we move one of the v8 pair into into the pod namespace, right? And then what we do is we also wire those two together, right? So we create the v8s, we bring them up, move one into the pod namespace, and then wire them up together. And now, when the pod wants to talk, we also modify the route table inside the pod to point out that this v8 is actually connected to the v8 outside in the host. So whenever the pod wants to communicate with the outside world, the route table makes it possible that it actually ends up at the host level. And then what happens there is, at the host, we modify both the main routing table, and we also have a routing table per ENI to make the communication into the pod possible, and outside the pod possible as well, right? For example, if a pod wants to send a packet out of that instance, we want to make sure that it actually goes out via the correct ENI, as well, because there could be multiple ENIs in the instance. And we also want to make sure that it ends up coming back through the correct ENI as well to avoid the asymmetric routing. So once we are wired up, so let's assume there's another EC2 instance, and when the packet wants to flow, so the pod sends the packet out, it reaches the v8 inside the pod, which ends up in the v8 host because we wired it together. And the routing table at the default namespace, what happens is it connects the v8 into the actual ENI, and then it goes out via that ENI that owns that particular secondary IP address. It ends up and the VPC fabric is responsible for actually routing that into whatever IP address that pod is trying to reach at. So things appeared really simple with what we did last time, right? And we said, no, this is too simple. How do we make it complicated? And we brought in IP tables. So the communication between pod and the external world happens because we modify the IP tables at the host level. So what we do is we tell the host that to source NAT to say that whenever a pod wants to talk to the external world, please use the IP address of the actual ENI to send out, which makes the return possible. So this particular CNI plugin is actually open source. We welcome all sorts of contributions. Please come over, file issues, talk to us about the features that you'd like to see us implement, or contribute to the code there, right? So we just released it, so take it as a beta quality and use it, give us feedback. So remember how I spoke about the limitation of the secondary IP address approach, right? So the security groups are actually attached at the ENI level, not at the secondary IP address level. So which means that if you want more fine granular security policies, you don't get it today with the security groups approach, security groups on the secondary IP approach, right? So we've collaborated with Tigera to make their Calico network policy implementation work well with our CNI plugin as well, right? Huge props to them. They've worked with us, and I mean, Tigera is one of the leading network policy implementations in the Kubernetes world, right? So we are super happy to have the support from them. All right, so next on to the actual Kubernetes and IAM integration, right? So one of the things we thought was, like, if you are going to offer AWS services, right? We are super proud of the security of our services, and one of the things that makes it possible is the IAM in the AWS ecosystem, right? So we want to bring that along into the Kubernetes world, and we were exploring options over there, right? And then came along Heptia's approach of using the STS to actually do the IAM authentication. We thought it's a great approach, and we wanted to collaborate with them, right? And what we have right now in EKS, the IAM authentication is made possible by the Heptia's Kubernetes AWS Authenticator implementation, right? So this provides native AWS access management solution as part of EKS. Both kubectl and the worker nodes are now going to talk to the master and authenticate and get authorized using the AWS native IAM methodology, right? And this works seamlessly with the Kubernetes RBAC. Like I mentioned, anything we do, we want to make sure that it works well with the existing Kubernetes feature set, right? And we were very clear from the beginning that we want to make sure that the RBAC policy implementation in Kubernetes works well with whatever we end up doing for AWS IAM integration, right? And this definitely works really well. So I want to talk about a little bit on how this works, right? So I'll break it down into 2 slides. One is how, excuse me. One is how user authentication works, which means, for example, kubectl. The other one is how the worker node authentication works, right? So when you provision an EKS cluster, what we do is we bring up the masters, obviously, and then we also bring up the AWS Authenticator webhook behind the scenes, right? And then connect the master to this particular webhook, which is an existing implementation in Kubernetes, right? So once we plug these 2 infrastructure in, right? So now you're able to use AWS IAM credentials. So as a user, when you create an EKS cluster, you automatically become the administrator of that cluster. And you, and only you, have access to that particular cluster, right? Which means that anything else from that point on, you need to explicitly authorize to let that through, right? So which means that by default, you don't have any of the EC2 instances, they don't have permissions to join into this cluster, which means that you have to explicitly go on and allow. So I'll talk about the worker node provision in a little bit, so which also applies to the kubectl. If you, as an admin, wants to provide access to another user, you would have to explicitly configure that in this implementation, right? So you'd use your kubectl, you'd use your existing AWS IAM credentials. The implementation we have right now in kubectl, what it does is it automatically gets a token for you to talk to the EKS cluster. It sends the token over to the Kubernetes. Kubernetes passes it on to the authenticator behind the scenes, which talks to AWS Auth and makes sure that everything looks good, right? So, and then once that user is authenticated, the Kubernetes RBAC policy kicks in, right? Kubernetes is going to consult that RBAC policy, make sure that whoever this user is able to perform or is authorized to perform the action he or she is trying to take here. So what happens for worker provisioning, right? Like I mentioned, to begin with, the only person who has access to this cluster is the person who created the cluster itself, right? So worker nodes cannot join by default. So the way you would provision worker nodes into this cluster now is you would go on to create a config map, which tells which instance role can actually be part of this cluster, right? You would create a node, you would create an instance role in IAM. You'd come and tell us that, hey, anything that with this particular instance role can now join into the cluster, right? So behind the scenes, the authenticator takes care of this config map, and then we'd also do an RBAC policy to let the worker nodes join the cluster, right? And then when you launch the EC2 instance, you would attach this particular IAM role on the EC2 instance, and then go on to launch it, right? As soon as you do it and point your worker at the master, it just magically works, right? So what happens in that flow is the worker assumes that role, sends it to, connects to the Kubernetes master. The Kubernetes master passes it on, it gets information, passes it to the authenticator. The auth verifies that, okay, fine, this instance role is a valid instance role assumed by the EC2 instance. And then the RBAC policy kicks in, right? Which actually says that anything assuming this particular instance role is part of the AWS instances group, which can actually perform any node-based operations, which means joining the cluster, accepting workloads, and so on and so forth. OK, so that pretty much covers the content. I'll do a pretty simple demo. So let me. Okay, so what I have here is, so I've pre-created a cluster and provisioned the worker nodes using the exact workflow I described earlier, right? Yeah. Is it better? Yeah. All right. So I've got a Kubernetes cluster created through EKS, so let me see how I. Okay, so Brandon demoed the console. So if you were to use the CLI, this is how the operation looks, right? So right now it's in preview, so it's at a different endpoint URL. So you would go on to create a cluster. Ignore the endpoint URL for now. You would go on to create a cluster. You would specify a particular cluster name. Like I mentioned, when you create a cluster, there are two important parameters that we expect, right? So one is the role arm, which lets us create resources in your account whenever you create deployments. Is that good? Is that good? Sorry, I don't understand. What are you saying? Make it bigger? Is that good? You guys shouldn't have partied yesterday. This is what happens. Yeah. OK. All right. So you would go on to create a cluster like this, right? So you would create a cluster. You would give it a cluster name. The two parameters we expect is the role arm, which lets us create resources in your account whenever you create container workloads, like, for example, the load balancer, EBS, so on and so forth, right? So, and then we also need the VPC ID to identify and manage the, to identify the nodes that are joining as part of, and which VPC we have to create the resources in, right? So, all right, so assume that I've done that. So I've got some nodes provisioned to begin with. So I have 3 nodes that are part of my cluster. Let me see what I have running. OK, so I do have a BusyBox image running. So I'm going to leave that right now. So I'll create a new BusyBox. So what I'm going to do in this demo is I want to showcase the actual networking. I'll also talk about the IAM authentication as well. I want to talk a little bit in depth about how the networking thing looks inside the EKS cluster, right? Inside the Kubernetes cluster. So in order to so I'll be creating a service. It's a simple Nginx service, and I want to get into the BusyBox pod and show that the networking works fine across pods, into the external world. And also, the DNS discovery works fine, right? So that's the goal of this particular demo, right? So right now, so I do have my AWS credentials in the regular place, right? So I have it there. So whenever I use kubectl, what it's going to do is it's going to automatically use the credentials in the usual place, and then talk to SDS, get a signed token, and pass it on to whatever request is being made to the master. And the master, once it, and then master passes it on to the webhook, which validates with the AWS auth. And then it makes sure that the identity provided is a valid user identity. And then what happens beyond that is Kubernetes consults as RBAC map to verify that whatever operation I'm trying to do over here, that particular identity is authorized to do that action, right? So in my case, that's the credential that was used to create the cluster. So like I mentioned, that particular credential has admin access by default, right? So I'm able to do any operation on that particular cluster. So I'll go on to create another BusyBox pod. So the network here is pretty wonky. So, all right, there it is. OK, so we have the one that I launched now running, right? So before I go on into launching the other Nginx service, what I want to do is I want to show the network. Yeah. So remember how I mentioned that you would create a daemon set to actually use the network plugin that we have. So I've already done that. And that actually flipped the node into ready status. And now you see that the AWS node, which is our networking implementation, is actually running across all the 3 nodes, right? So all right, now that I have the BusyBox pod, I want to get into, so let me do a describe. All right, so that pod got an that particular IP address, right? That is actually my VPC address. My VPC has a CIDR at 10.0.0.0/16. So that's part of the VPC space, right? So you get a native AWS IP address. And then what I'm going to do is, so given that secondary IP address, I can connect to it, right? So it's internal, right? So I do have a public IP for that particular node. I know which node so it's running in a particular node here. I'm going to log into the node to show what's happening over there, right? So. Right, so I'm actually in that node. Okay, so that's the pod that's actually running in there, right? So remember, it actually got a 126.161 IP address, right? So remember how I mentioned that we modify the main routing table in the host. We also modify the ENI-specific routing table to make the communication into and out of the pod possible. And we also modify the routing table inside the pod to wire the reads together, right? So, so if I do IP route show, so that particular IP address is configured to go through that particular ENI, right? So. All right, so I do have an ENI in there, right? So, so what I want to show is I'll exec into that container. Right, so I'm right now inside that particular container, right? So if you look at the, so in the IP route table inside the pod namespace, what you see is it actually sets up a default gateway at that particular IP address, right? And then we configure a static ARP entry to hit that MAC, right? So if you go back outside, there. If you go back outside, that particular MAC and belongs to the ENI over there, which is what we wired the pod IP address to use, right? So that's how the networking actually gets wired up. All right, so that's the networking part of the demo. I'll go on to show the actual network communication, right? So I'm here. I've launched a BusyBox pod. So I'll go on to create an Nginx service. Okay. All right. All right. So let's make sure it's running. Yep, everything is running fine. Yep. So I'm in the node where the pod's running, right? So I'll get into the pod one more time. So that particular Nginx deployment has 2 pods running, a replication controller with 2 pods. And we have a service by the name of my Nginx, right? So I'm inside the BusyBox pod. I'm just going to show hitting that particular in-cluster service. And see that everything works fine, right? So the pod-to-pod communication works fine. I'll also do a pod to external world request. There. So what you saw is so the pod's actually hitting the DNS, getting the DNS resolution working, right? That's working, and then we are able to get to the external world, right? So all the things that we did, including the IP tables, is what makes this particular networking implementation fly through like this, right? So it's working at pretty much the VPC speed because we're not in the data path at all, and that's all I have to show you today. So that's the demo. Right, can we have Arun and Brandon here, please? We're happy to take any questions you have. So Arun is our open source specialist, and Brandon is our product manager. So, and we're all representing our team, who is in Seattle right now. So,
check, check, check. All right.
And we should have someone running around with mics to answer questions. Nate in the back.
So we have Nate and we have Asif who can running on the mic.
Does it work? No. Oh, yeah. All right. Okay. How quickly will you integrate with new versions of Kubernetes? Because you guys are only running 1.7 right now from what I saw on your demo.
Yeah, that's correct. So the previews is 1.7. We're currently working on qualifying new versions. We've already started the work with some of our internal teams, like our AppSec team, for example, to make sure that anytime a new Kubernetes release comes out, we can look for vulnerabilities, make sure everything looks good, and get it qualified as quickly as possible. So I don't actually have how quickly can we do it, but we're setting up all the processes to make sure that we can do it as quick as possible.
I have two questions, kind of. It sounded like with the Kubernetes CNI plugin that Kubernetes network policies wouldn't work because of that separation. Is that correct?
So we're working with Tigera to make the network policy working with CNI, right? So
that's what
you'll see it.
Stuff like that.
Yeah.
If you've seen the Canal project, which is Flannel and Calico working together, so Flannel for networking, it's a very similar approach with our CNI plugin.
The next quick little thing would, for DNS inside the cluster, are you guys using kubedns? Is that set up for you, or do you leave that up to for in-cluster service discovery, or do you tie that to Route 53 at all?
One more time, sorry.
For the DNS within the cluster,
yeah.
Are you using the default kubedns?
Yeah,
is that set up for part of the master plane?
Yeah. It is kubedns.
Okay.
Yep.
Hey, I also have two quick questions. First, does the new CNI plugin by chance support any node-to-node encryption?
Node-to-node encryption is what you said?
Yes.
No, right now there's no. It's just pure IP there. There's no IPsec there.
And second, based off of how the integration with all the additional ENIs works, does that mean that there is a hard limit on how many pods can run per node based off of the ENI and secondary address limits on EC2 instances?
You want to take it? Yeah.
Yeah, so if you look at there is EC2 documentation that tells you like how many ENIs you can attach per instance type, and then how many secondary IP addresses you can get per ENI, right? So on larger instances, you probably wouldn't have a problem because on like an 8XL, you can have 15 ENIs and then I think 40 secondary IP addresses per ENI. So it's a pretty decent amount of pods you can schedule. But the CNI plugin is also aware of like those limitations. So we'll attach as many ENIs as we can on a given instance type. But you will have to be a little bit cognizant of like, you're not going to get 100 pods on a T2 micro, for example, probably for other reasons besides network density.
So just want to acknowledge the team's work. This is good stuff. Recognizing that this is a deep dive in an advanced session, my question relates to if you can comment on Fargate and where that may enable a developer without a deep understanding of Kubernetes to have a private instance or private cluster. Just curious your thoughts on that, and recognizing, of course, that product I think they said was going to release next year, but just trying to see if you can comment on again, enabling developers to have a simple cluster of their own.
So to make sure I understand, your question is basically, so with Fargate and EKS, can you make sure that like there's isolation around the cluster and you don't have to worry about that if you don't have deep understanding of Kubernetes already?
Yeah, exactly that, right? So in our cases, a lot of our product teams have individual accounts, separate management, lots of things like that. So they're not going to, this would be a big leap for them unless the ops organization provided EKS directly as a service. Fargate may be an enablement, right?
Sure. So all the details about how Fargate works with EKS are obviously not yet set in stone. And I'm also going to speak a little bit out of my depth about Fargate here, but the isolation boundary is the cluster today in ECS with Fargate. So I don't see any reason we want to break, some of the goodness that is baked into that model today, but it's probably too early to comment in any depth on that. I think we're definitely cognizant of like the security requirements around making this work and making it easy for you to get something that's kind of secure by default.
And that's
So,
exactly,
good question.
yeah, that's exactly the point right there. Thank you.
Is it possible to assign IAM roles to specific pods and have different pods with different IAM roles?
So, yeah, so today, if you look at it, the way IAM roles is done, there is two aspects. One is on the kubectl side of it, where you can actually give an IAM role to the authentication to your cluster. But come on the runtime side, where you want to assign an IAM role, we see our customers using kube2 IAM, for example. Now, we are aware that kube2 IAM has issues, like things like assume role and all. Another aspect that we have seen our customers using is HashiCorp Vault, for example, which allows you to generate temporary IAM credentials and then apply it to a particular pod when it's running. But that's something we are looking at it, whether we should contribute to kube2 IAM itself, make it better, more secure, more safer, or we look at another alternative, which is much more baked into EKS itself. The key premise is going to be that it's going to be done in open source. And as Isper said, you can bring your own Kubernetes to AWS, and then that's what we will use in EKS as well.
Can you speak to the preview? How many customers are in preview now? How open is the preview going to be? Any kind of time frame?
I can take a shot at that. Right now, we are working on, so the preview currently is a bunch of internal customers and then customers we've worked with, over the period of research and development for this product. So it's a very kind of specialized subset currently, and the best I can tell you right now is we'd like to onboard customers as quickly as possible. I'm trying to set realistic expectations that, if you're sitting in this room today and you're not already talking to us about it, think 2018, so probably not December. But again, the whole idea of previews here is that, what we learned during preview is how we can scale this and operationalize it and, make sure that those lessons learned let us scale up the size of the preview really quickly and get as many people onboarded as possible. So that's our goal, but I can't comment anything more concrete than that right now.
Hi. I know it's early days, but what about cross-region cluster federation? Is that on the roadmap?
Man, federation keeps coming up. So this is such an interesting topic because some customers have told us, like, we're staying far away from federation. Some customers are really interested in it. The definitive answer I can give you right now is, as far as I know, it's still an alpha feature.
Right.
And so we don't intend to support alpha features on our clusters currently, unless that becomes a major deal breaker for a lot of customers as well. So this is still something that's in flux, and we're watching that space currently. But I think for now, it won't be supported. If you really need it, let us know, and we'll work on getting there.
Yeah, also, if we look at it, the federation part of it, you look at KubeFed, it's pretty flaky right now. To be able to set up two clusters that are federated across two different regions, for example, is not easy. Even though, the steps are documented, but it doesn't work all the time. It's not very reproducible. So that's sort of the flakiness part of it. And then the federation architecture within Kubernetes is also evolving. However, what we see our customers using is setting up two clusters in the backend, using sort of a deployment pipeline, either using Code Pipeline or Jenkins or whatever your favorite CI/CD tool is. Take an app, say deploy to region 1, deploy to region 2, and then get it running that way. And that is also critical for them as opposed to federation, because that gives them isolation in a particular region as well. So that's also important for our customers.
So one more thing I want to add is we enable only stable and beta features right now, right? So, and it's a pretty opinionated master setup, right? So we are looking into how we can provide more knobs to customers to tune the master, and that'll come down the line.
Does the networking for EKS limit the use of something like Istio or the Envoy sidecar pattern?
Sorry, Who am I talking to? Okay, there. I was like, yeah, I was looking at it. Sorry. Can you repeat one more time, please?
So the networking that you've done for
Yes.
EKS,
Right.
will that limit the use of something like Istio or a service mesh with Envoy as a sidecar pattern?
No, it
doesn't
shouldn't.
get in the way
Nope,
at all?
No, it should just natively work.
Okay.
Yep.
I think one of the key things that you want to understand this is, if something is working in upstream, if you are running your own Kubernetes cluster and you can do that over there, you should be able to do that over here. The only limitation would be is because it's a managed service, you cannot apply any random add-on to the master. And from our side, we will provide a few set of add-ons that we make sure that work well with our managed service. And then, but the worker nodes are going to be on your control, so you can do whatever you want to do on your worker node.
Question around how this integrates with the rest of the kind of AWS ecosystem. For example, if you created a service with a type load balancer, would it automatically spin up an ALB or an ELB, like some of the other systems out there?
So today we leave the ingress controller to the customer because it's going to run in your worker node, right? So you're free to use whatever is available in the community, right? But having said that, we think that we could make some improvements to the existing implementations out there, right? Maybe add the features that are missing in the actual controller implementation that are available in our AWS service, and that's something that we'll be investing more.
So the NLB support as the default load balancer type for services of type load balancer was recently upstreamed. So that pull request was recently merged. So the NLB will probably become the default for layer 4 load balancing in AWS going forward. So I think that's going to be in 1.9? 1.9. So that'll gradually phase out the classic load balancer. The ALB maps really well because it's purely L7, maps very well to the ingress concept. So there is that ALB ingress controller from CoreOS today, which doesn't have complete feature parity with the ALB currently, but that's easily resolvable and something we'll work on.
Great, thanks.
Is supporting node-to-node encryption on the roadmap, and if so, how soon can we expect to get that? Like node-to-node network encryption.
So because we're using VPC, like native VPC networking, we would need to probably drive that feature with the VPC team.
Yep.
So I don't actually have enough information to comment on that, but it's been mentioned a couple times here, so clearly it's important.
Is pod level security groups on the roadmap? Pod level security groups, basically attaching a security group to a pod instead of the EC2 instance.
Yeah, so that's also kind of a limitation of the underlying platform in that the security group construct is built around ENIs. So until that's resolved in the underlying platform, for example, we wouldn't be able to implement that. So the idea here behind the network policy implementation with Calico is that you can do all the granular security policies at the Kubernetes API layer instead of having to think about the underlying AWS abstraction. There probably are ways we can kind of tighten that up, but the limitation is actually at the AWS VPC level and how security groups work today.
Yeah. But we are aware of that, and we are engaging with the actual security group team to make that possible as well, right? So.
Okay. Does the worker support auto-scaling?
One more time.
The worker support auto-scaling or not?
Yes, so the current Kubernetes auto-scaling mechanism, so like the cluster autoscaler or the horizontal pod autoscaler, both work and run on your worker nodes today. So we'll handle scaling the masters for you, and you won't really be aware of that. We'll just kind of handle it transparently. But the worker nodes, you can bring existing scaling mechanisms in Kubernetes, and they'll work.
It was exactly my question. It was the same.
Oh, there's a question here. Nate.
Okay, so if I can, one of the inconveniences for me is that I need to have, like, for every subdomain for ELB, I have to have one ELB because of the SSL certificate. Are you guys going to fix this in some time?
I am, but this is something that we have to take it up to the ELB team, right? So I'm pretty sure they hear this feature request a lot, right? It's something that we can't comment on at this point.
We have Kubernetes already running right now, and you said the workload should be able to run on using the managed master and the XD cluster. So what about infrastructure code? We build node and all that stuff. We control security group, you know, all the ELB, all the VPC, routing table. And would that, if we make changes, that will interfere anything? And the Kubernetes also rely on a lot of tags, right? I mean, in the open source way. Are you using the tags also same way to manage the nodes?
So given that, if I understand your question right,
yeah.
right? So correct me if I'm wrong, but given that the worker node is entirely in your control, right? You're free to do whatever you want, right? Tagging, right? We do add some tags to it, but if you end up adding tags, that shouldn't mess up with anything in our management side.
So one of the things that we also hear around this topic also is, like, what we will do is we will provide you a pre-prepared armies. You can take those armies, and that's when you're going to deploy them as a worker node. But what we'll also do is we'll also open source the Packer scripts on how we create those armies. So for example, let's say you don't like our army for some reason, then you can use those Packer scripts to bring your operating system, package the worker node exactly the same way, and say, use this as a worker node instead. So whatever you want to do in those worker nodes, however you want to create that army is entirely up to you. But that will still connect to the master, essentially.
So I'm more about infrastructure level, like VPC, security group, and all these are actually built by our own code. Would that get interfered with these managed clusters?
Well, I mean, when you are creating the worker nodes, you will have an option to join, use an existing VPC ID, essentially. So all that would be like, leveraging your infrastructure, essentially.
Yep.
Do you have any plans to integrate CloudWatch alarms with horizontal pod autoscaling?
Horizontal pod autoscaling? Yeah. That's one of the beauty of EKS. It's 100% upstream, so anything that is in upstream would work here. So what I would like to do is I would like to pitch a workshop that we have been working for the past few months. If you go to github.com/AWS-samples, there is only one Kubernetes workshop over there. And in that workshop, anything that you could think of in terms of app scaling, metrics, logging, monitoring, CI/CD, developer concepts, whether you are new to Kubernetes, whether you are advanced in Kubernetes, we have a whole lot of design patterns. And literally, I don't believe in too much manual reading. So it's like drag and drop, copy, paste the code, and get rolling with that. So take a look at that. That actually has an example for how would horizontal pod autoscaling work. Today, that workshop uses COPS. It's using a COPS-based cluster. And essentially, when EKS goes GA, we'll add a section, provision your cluster, but 90% of the workshop would still be relevant because essentially teaching using Kubernetes on top of AWS. But all the AWS integrations are there.
All right, great. I have one more question. Is there going to be any support for multi-tenant networking within the cluster?
Can you expand on that, please? What do you mean?
So just having tiers that are segmented and like namespaces that don't allow communication between each tier.
So that should work with existing Kubernetes network policy implementation, okay. Right? So which means that, I mean, that's the one that we mentioned about working with Tiger, right? Mm-hmm. So that would enable you to segment your network communication as well, right?
All right, great, thank you.
So you're saying, or you're showing that you can spawn the cluster in an existing VPC. Do you also set up some subnetting stuff? Because you have to choose your IP address or your IP ranges very wisely. Because if your subnets are too small and each of the pods are becoming private IP addresses within the net, you have to be care so that your subnet is big enough.
So today, when you give VPC ID as part of the create cluster thing, right? So the only thing we use that for is to create resources in your cluster when you create deploy. Like for example, you created a load balancer using an ingress controller, or you wanted to create an EBS volume as part of your stateful set, right? We don't create any subnets or any worker nodes in that particular VPC subnet. Is that clear? So that's entirely in your control.
Yeah, but the ENIs, the IP address of the ENIs are within the subnet, right? Within the VPC, right?
Correct.
Right. So
right.
You have to choose your IP range
right.
Big enough to spawn at least 5,000 nodes or something.
That is correct.
Okay.
Right.
So I think the important way to think about this is it's no different than like provisioning EC2 instances in the VPC today, right? So you still have to think about what your subnet size is, but you might want to think about like over provisioning it in some cases because you're going to have more IP address density on any given instance instead of just like one or two on an instance, because every pod gets its own IP address in this case. So the way that like we have set up some of like the default CloudFormation or the CloudFormation templates for spinning up default worker nodes, we use like /19s, for example, to give you a little bit more space in each subnet. So it's just like the same considerations as using EC2 networking today, but with increased pod density as part of your considerations. Does that make sense?
Yes, I'm just asking because normally if you have some kind of CNI overlay network like COPS did, for example, you are more flexible because the number of nodes or the number of IP addresses within your local VPC are less than in compared to if you have an ENI with an IP address within your net. So, yeah, so that's why I'm asking. Okay.
Yeah, so the trade-off in that case, so using an overlay network gives you, an IP range that's outside of the VPC, which comes with its own complexities, of course, right? So in this case, you do just have to make sure that the network that you're actually using, which is the VPC, has sufficient IP address space for all of those pods, right? Yeah, good question. Very interesting.
What about the life cycle of the nodes, of the master nodes? So do you have a plan for that, like upgrading and doing all the stuff?
Yeah, that's probably something we need to address. So, there's kind of like a multifaceted answer to that question. So for like Kubernetes upgrades, for example, we don't actually need to control the life cycle of the EC2 instances to do like rolling upgrades of Kubernetes versions on those instances. But if it becomes like a really important feature for customers, like you want to be able to use EKS APIs to control the life cycle of the EC2 instances that run as worker nodes in your account, that's something we're completely open to. We've looked at a few ways to implement that already. So it just doesn't exist today. We could build that. It just depends on, do you want to use EKS APIs for that, or are you okay with using existing like EC2 and autoscaling APIs for that?
I'm asking specifically for the master nodes, right? So are you going to take care of upgrading from 1.7 to whatnot?
Oh, yes, absolutely.
Now, the other part you also want to understand is like, and that's going to be either automatic or manual, so you'll be given a choice. But then if you're looking at, say, 1.9, for example, or 1.8, if there is a minor release that happens, like 1.8.1 happens, so then we will automatically upgrade. But if you go to a major release like 1.8 to 1.9, so then you will have control of that. Because minor releases typically have CVE, security patches, so we want to make sure you're not bothered by that.
I have a question about autoscaling. So for ECS, to do autoscaling, when it's scaled down, you have to add additional code to do the draining. For Kubernetes, does it handle that, or do you have to basically write additional code?
No, you can do that in Kubernetes as well, right? So you can actually cordon and remove the node from getting pod schedule of that node, and then you can take it away, and then it continues to work seamlessly.
So and that's a very Kubernetes concept, actually. You drain the node and then you bring the node back up again. So it'll very much work in that upstream manner.
Okay, so it takes care of that for you then.
Correct.
Great. All right. Thank you.
There will be any way to have direct access to etcd?
Can you repeat that?
Is it possible to have direct access to etcd?
Oh, access to etcd.
I see.
Well, that's the whole joy of managing it. Do you really want access to etcd? That's one of the main reasons we are building a managed service here, because managing etcd is not for the faint of the heart.
Actually, yes. Having at least read access to etcd is the most important thing you may have.
We should maybe talk offline on what your exact use case is to understand why you're actually looking to access the etcd, right? So is there something that we should be doing differently to give that particular information you're expecting to get, right?
So one of our perspectives right now is that we've noticed a lot of projects in Kubernetes moving away from talking to etcd directly and instead going through the Kubernetes API. So we want to make sure we can accommodate your use case, but we need to definitely understand that and dive deep into it.
Yeah.
I have a question basically related to the resources that are managed by Amazon, right? And do you have any numbers related to the performance and availability of the masters? And the second question is, will we, as the users, experience some kind of latency when we hit to the master? Something similar that we often can see when we, with services like Redshift, right? You do first hit, you wait for several seconds, and then you get the response.
Yeah. So we don't have numbers to share at this point about the performance and the availability numbers for master, right? So we'll share it when we have those, right? So regarding the performance impact, right? So we haven't run across any performance impact right now, right? So there's literally an ELB in front of the master, right? So so you just directly, but there's a very thin layer there, right? So you hit the LP and then you hit the master, right? So.
Okay. Do you have just, I don't know if you can share like unofficial statistics, like how many pods or how many worker nodes you were targeting during your
so we'll make it available when we have the number for sure.
So one of the things over there is like we're looking at whatever Kubernetes' requirements are. So Kubernetes SIG test says when you're making a worker node, it should be scale up to 5,000 node cluster. So that's essentially what we will do. And if there are discussions in SIG testing to change that from 5,000 to 10,000 nodes. So whatever those requirements are, we will meet that. So with that, pretty much time up. I know we can keep talking. We are excited. I'm sure you are excited too. Yeah. We can keep talking about this topic. Please reach out to us. Please talk to us. We would love to hear more from you. Thank you very much.
Hey, we appreciate you coming over here, right? So thank you, guys.